Thank you. Thank you very much, Paula. Well, thank you, everybody. Thank you for the organization. That's a long time ago that I didn't do a workshop, so I'm very glad to be here. And that's a totally new project. I mean, the icy moon are new for everybody, maybe, but for me, it's very, very new. And I'm very glad to present some zonal jets in the icy moons. So it will be about zonal jets this afternoon, if I understood well. Well, I'll try to be quick on the introduction, but of course, I'm the last one to talk about the icy moon, so I also have a quick introduction, but it will not be as good as the one of Krista, but let's have a quick overview on the icy moon, and just to rapidly say that most of what we know has been collected by Galileo and Cassini-Huygens, and that in 1996, Galileo had his first close encounter with Ganymede and Europa, and it came within approximately 200 kilometers above the surface, all right. And it provided various data, the mass radius, the mass of the planet, the gravity, magnetic field, surface temperature, et cetera, et cetera. And thanks to the gravity field, we know today about the existence of these three-layer planets, right? A water layer on the top, a rocky mantle in the center, and a metallic core, a rocky mantle in the middle, and a rocky metallic core in the center. However, the very small density contrast between ice and liquid water does not allow us to distinguish between them in the gravity measurements, but we know that there is subsurface oceans, of course, because of the plumes which are coming up across the surface. But one of the best evidence we have about that comes from the magnetic fields and magnetic field perturbation in the flyby of Galileo along his flyby here. So you can see here the red data of the magnetic fields. And of course, the magnetic field can constrain what is the typical electrical conductivity, but also provide insight into the thickness of the oceans, because ice has very low electrical conductivity, while liquid water demonstrates higher conductivity, of course. And Schilling has demonstrated that along this Galileo flyby, these data require the existence of a near-surface conducting layer. And I'm very interested in this magnetic field signal, as some of the perspective of this talk today will be about the induction of a magnetic field from the oceanic circulation. And this constrains the conductivity to be about 2 to 5 Siemens per meter. If I remember well, this is not only the constraint from the magnetic field, but also from the chemistry which have been captured at the surface of these icy moons. And solving the inversion problem to try to fit these observations with magnetic models is always a trade-off between the conductivity, that's why there is some error bars and a certain range of conductivity, and a trade-off with what is the thickness of the oceans. And it is about few hundred kilometer depth. It could go to 500 kilometers depth for Ganymede. So it's a huge amount of water, of course, and that's such an abundance of water positions those moons today as primary targets in the search of environment with potential habitability. Well, we all know that there is 2 new space missions now scheduled, the JUICE from ESA, Europa Clipper from NASA, that will be dedicated to the study of those moons. And because, of course, there is not only water on those moons, but various salt, silica, nanoparticles, sulfurs, even organic, I think, have been detected at the surface of the icy moons and in plumes erupting from the surface. All right, and this evidence a substantial hydrothermal activity at the bottom and also very well mixed oceans and oceanic currents, likely driven by thermal convection, but it could be also some other mechanical forcing or double diffusive convection, etc. So the question of that talk today is to understand what is this oceanic circulation below the ice crust. It's fundamental to constrain this habitability and to understand how the bottom of the ocean is connected to the upper ice crust and the observation that will be made at the surface. So that's the today question of this talk. And I mean, a lot is known already about this oceanic circulation because various studies have started to simulate those flows. And I would say that most of what we know today relies on numerical simulations of thermal convection in rapidly rotating sphere. And all those studies evidence or suggest at least the presence of planetary scale circulation below the ice crust, forming what we call those zonal jets, so this axisymmetric flow, which is dominated by the east-west velocity component. However, there is still huge discrepancy across the different studies. It's difficult to attribute or to distinguish which flow pattern could belong to the different moons. It's very hard to distinguish them because it depends on the thickness of the ocean you choose for the simulation. It depends also on the boundary condition you are choosing for those simulations. So is it a two-jet solution, a multiple-jet solution? It's very hard to distinguish between them. Also, velocity predictions differ a lot from across the different studies by a few order of magnitude. And we need more constraint today about that. We need to go further in our understanding of those differences to try to get better predictions. So what I will suggest today, it's, let's say, a three-panel presentation. I will go through a little bit of theory about rotating turbulence, and I will introduce the concept of zonostrophic turbulence, which I hope will help to uncover the dynamic of those flows. I will validate this theoretical approach with some numerical modeling, and I will open some perspective about a magnetic signal coming from this oceanic circulation. So let's start with a little bit of theory. What is interesting with the zonal jets, you all know that they're ubiquitous feature in nature. You can observe them, of course, we have seen this morning in Saturn and Jupiter. Even if you average in the atmosphere of the Earth, you will find some components which correspond to zonal jets. Even in the Earth's Pacific oceans, in Venus, I mean, the list could be even longer, but what is interesting here is that thanks to this atmosphere and oceans, we can directly confront any theoretical approach with direct observations, and eventually then apply this theory to the subsurface oceans that we cannot directly observe. So that's pretty much the strategy of today for me. It's to take advantage of a theory validated by observation to uncover these dynamics. And there is few steps to reach that goal. The first one will be to try to identify which are the dynamical ingredients which are constitutive of zonal jets. And this is pretty much what we have done with John when he came, it was 10 years later, I think, in France, and we set up an experimental device to reproduce the formation of zonal jet. That was the purpose of that. And to do that, we identify three typical dynamical ingredients constitutive of those jets. So the first one is just an energy input. Of course, you first have to drive the flow to turbulence, and I call it pi. It's just the power of turbulence you are injecting in the flow. I call it pi because it can be baroclinic instabilities, it can be mechanical forcing, it can be thermal convection. I just want to have a power of turbulence injected in the flow. That's why I call it energetic input. However, once you have three-dimensional turbulence, you all know that this leads to classical turbulent cascade and transfer kinetic energy from the injection scale down to viscous dissipation. And in this typical 3D turbulence, you have no bigger scale than capital L, the injection scale. But we all know that rotation can reverse this process and transfer part of the kinetic energy to the larger scale because it makes the flow invariant along the rotation axis. It makes it quasi two-dimensional, and then you can grow large-scale features, as for example here, this beautiful vortex. And so that's the second ingredient, okay? You have to drive the flow to turbulence, you have to rotate it, and the third one, of course, it's to impose a gradient of potential vorticity. And the best way to do that in the lab is just to deformate the free surface, and you will have this so-called beta effect that will not only grow large-scale structure, but preferentially channel the energy into the zonal direction. So you grow large-scale structure and you make it zonal because of the beta effect. All right, and thanks to these three dynamical ingredients, you can reproduce, that's the recipes for jets, and you can reproduce jets as you observe them in the atmosphere of Jupiter. Okay, so that's the first step, and once you have the ingredients, you want to know what exactly determine the typical length scale of those jets, what determines the typical velocity of the jets, and the typical kinetic energy of those, and all the stuff that you want to know once you get a beautiful device to reproduce them. Well, I didn't show you the exact results of how we did that in the laboratory experiment, but I prefer to introduce direct observation, and this is a study from Boris Galperin which have been extended by other studies. And they were using a very beautiful technique, which is cloud tracking from images of Jupiter. So they have various images of Jupiter taken from Cassini mission. And they can compute, thanks to a cloud tracking, some velocity map of the flow. So here you have the east-west velocity component, and here you have the meridional velocity component. So you retrieve this beautiful jet. You have this great red spot here and other vortices. So they're a very beautiful map. And when you have in the turbulence field, you used to plot some kinetic energy spectrum. So you just plot from those maps kinetic energy distribution as function of wave number, where each wave number corresponds to a typical length scale of the flow. And what they suggest to do in that study is to first represent what is the contribution of the axisymmetric part of the flow to the distribution of kinetic energy. So basically what I show here is just the energy of the axisymmetric part of the flow, and they usually call it the zonal energy. So basically this corresponds to the energy of the jet. And what they show is that they find a very beautiful scaling which goes in beta square k to the -5, which means that it's very steep spectrum here. And the magnitude of the zonal energy is given by this parameter beta, which corresponds to the typical parameter of the planet. It has nothing to see here with the energy input, but only with the rotation rate and the radius of that planet. All right, so that's a nice first prediction. And then you want to know what is the other part of the flow. So they call it the residual energy, and this corresponds to everything which is non-axisymmetric in the flow. So everything which is not the jet. So basically the waves and eddies and all turbulent motions. And here in that distribution, they retrieve this typical slope on the small scale, which corresponds to this very well-known Kolmogorov scaling, which goes as k to the -5. And here, the magnitude of the residual energy corresponds to this pi, the energy input in the flow. So basically, in the atmosphere of Jupiter, this corresponds to the turbulent mixing that you can observe. All right, so that's a first good step. What we can project also on that kinetic energy diagram is two typical length scales to conclude that story. Here I do report what will be the baroclinic instability typical length scale in Jupiter. I mean, you could have some other source of energy, like thermal convection could be part of those. Baroclinical instability as well, so this is just the direct transfer of solar energy into baroclinic eddies. And in Jupiter, a typical baroclinic eddy will correspond to this KF typical wave number. And the other length scale, which is well known as well, is known as the Rhine scale, and this represents the typical size of the jet. And this depends on the beta parameter and U, the typical flow velocity. So that is what they call zonostrophic turbulence, and the zonostrophic turbulence is just the combination of those two spectra, the one of the zonal energy and the residual, and you're zonostrophic when the zonal jet corresponds to the most energetic features in the flow, which dominate over the residual counterpart. Maybe to sum up here, or to understand a bit better what is the dynamic behind this kinetic energy distribution, we can sum up the thing as follows. Kinetic energy is injected at those scale. Then kinetic energy is transferred upscale up to the jet scale, where it is finally dissipated by large-scale friction. And in the case of Jupiter, we have seen that morning that this large-scale friction is likely corresponding to the bottom magnetic drag. And this is this large-scale friction which arrests the upscale energy transfer at the size of the jets. All right, so this zonostrophic turbulence is a comprehensive theoretical understanding of what is the kinetic energy distribution in those flows. And it's quite a robust approach because we have found this kinetic, yeah?
Just to clarify, the U in the Rhine scale, that's RMS?
Yeah, that's RMS. Well, yeah. Some person take the typical velocity of the jets, others take the RMS of the full velocity in the bulk, but yeah, that's the RMS. Usually, yeah. So here I show various approaches in which this kinetic energy distribution have been retrieved, of course, in the atmosphere of Jupiter. Here is just a global circulation model, which have been adapted to the atmosphere of Saturn. I should have noticed Saturn, but this is Saturn. And, well, it's a global circulation model which have been adapted with the orbital parameter of Saturn. So that's the typical climate of Saturn. And you can also retrieve this kinetic energy distribution quite well in the atmosphere of Saturn. And you can then estimate what will be the typical turbulent mixing in the atmosphere of Saturn by estimating this pi value. And Daphne also designed a laboratory experiment which is very similar to the one I presented in the introduction. And she also retrieved very well this k to the minus 5 and k to the minus 5 third. And the Rhine scale here point in the direction of the maximum of zonal energy. So just to say here that it's a pretty robust theoretical scaling that works in different setups, even in the observations. And now we want to know if we can apply that to the subsurface ocean. So to end, yeah?
Yeah, so when you talk about Jupiter, you're saying a large-scale dissipation is provided by the magnetic field. In the numerical simulations you showed in the middle panel, what provides the dissipation?
Yeah, here dissipation is given by something which mimic the magnetic drag, and it's a turbulent drag. It's an analytical turbulent drag, which is added at the bottom of, it's a alpha U cube. At the one that Wang Kang has presented concerning the model of the Earth ocean. Do you remember there were a drag coefficient that you calibrated? And then there is U cube, so it's a typical turbulent drag, which is supposed to mimic energy dissipation at the bottom.
Can I ask a quick question?
Yeah.
Which you might not know the answer to, but when these things have been kind of gone out with observations, is it that you're able to infer an injection scale that's consistent with spherical instability?
Yeah.
Or is it just that there's, at some small scale there's energy injection, but it's actually hard to tell where it occurs?
That's the typical Rossby deformation radius in the atmosphere of Jupiter. So it's an estimate from the Rossby deformation radius, which gives you...
But if you took the arrow off in the actual spectrum, can you see any evidence of, that's where energy injection is happening and afterwards the slope is different?
Yeah. In one of the studies, they computed the energy flux. And you can see that if you represent the energy flux here, you see the inverse cascade, so a negative energy flux, which transfer energy upscale from approximately that scale. And from this scale, you can see a positive energy flux, which is showing a downscale cascade, energy cascade. Yeah. So yeah, this estimate corresponds very well to this transfer. To this inversion of the cascade. Yeah. Okay, so let's investigate the possibility to have this scaling in the subsurface ocean. So here, I would like to first introduce a Rossby versus Ekman diagram, so inertia over Coriolis and viscous forces over Coriolis. And I also report and locate the different planetary atmosphere on that diagram. And I would like to first introduce two typical boundaries. This one I just put Rossby is equal to 1, which suppose that above that boundary we're under weakly rotating condition, while below you're under rapidly rotating condition, including Jupiter, Saturn, the Earth oceans, and to a lesser extent, the Earth atmosphere and Mars. This boundary corresponds to the weakly nonlinear regime, which means that the flow is not energetic enough to transit into turbulence. And now we want to plug in that diagram what...
How do you define that boundary?
This one?
Yes.
Well, it's just, I reported it from the onset of convection. Below that there is no convection, and I had a Rayleigh versus Ekman diagram, and you'll see that I had some numerical simulation, and below that there is no turbulence from the convection, and above this one you get convection, so you get turbulent convection. It has been determined by the numerical simulation, which will come afterwards. There is no analytical, well, yeah, you can estimate. So here are the different icy moon and the subsurface oceans, along with their current uncertainties. So these uncertainties are regarding the different flow velocity prediction and the uncertainty on the ocean thickness as well, D here. And you can see that there is quite a huge uncertainty across the different studies I found about that. They give various predictions for the typical flow velocity. Yeah, Krista?
Yeah, for the velocity, is that just a zonal component or a convective, or what are you considering for the velocity?
Well, it depends on the study. There is some study where they say that it corresponds to the zonal velocity. I just took all the prediction that I found. Some say that it's just the typical large-scale circulation. Others say that it's exactly the zonal jet. It depends. I just compiled all the typical velocity prediction I found. That's why I have this huge uncertainty here along the Rossby, but as well you can report the uncertainty here on the thickness of the oceans. So we would like, thanks to the geostrophic scaling, reduce those boxes. That would be wonderful. But to do that, we first have to answer if the geostrophic turbulence can be applicable to the subsurface oceans. And this needs to be checked, actually, because it's not sure that in this typical dynamical configuration, which is quite different than the one of the gas giant, here you have, of course, thermal convection, but you have no slip boundary condition at the top and bottom. And in the gas giant, you have free slip condition at the top. So let's verify, let's check if we can retrieve this scaling in the typical dynamical configuration of the subsurface ocean. And to do that, of course, you have to go through some numerical modeling. We might do some stuff in the laboratory as well, but first of all, I'll go through some numerical modeling. And let's be back with my Rossby and Ekman diagram, and let's first report some of the previous studies that have been conducted on that topic. So some from Krista Söderlund, Vorka, and Hamid, and respectively with the boundary conditions they've chosen, free slip for FS and NS for no slip. Yeah?
And in those simulations, is that an input Rossby number or an output Rossby number?
Well, that's a good question.
Because you're comparing it to the output Rossby number of like the Earth or whatever else.
I think I recomputed for all of those, because in the paper I have an Rayleigh versus Ekman diagram. I just computed the Rossby versus Ekman just because, I wanted to have this Rossby number. And I think I recomputed the real Rossby number for each of those simulations. Yeah. I think you can find in all of those papers a way to find this Rossby number. It's not always easy, but...
So these are all outputs?
Sorry?
So these are all output Rossby numbers?
Yeah. Output, yeah. Exactly. And of course, in this planetary flow, viscosity is very low. So it's very difficult to implement in the numerics. That's why they do not exceed the 10 to the minus 5 value here. All right. Well, in this context, it's very difficult to know what to do with the boundary condition. Of course, no-slip boundary condition may exaggerate the viscous stresses and the dynamic. That's why Krista and somehow Vorka have opted for this free slip boundary condition. But then when you do that, of course, you suppress the large-scale dissipation that operate at the boundary. And that's, when you look at the inverse cascade, you feel that you need something to stop the inverse cascade. Otherwise, you will grow large-scale zonal jet almost indefinitely, and it's very difficult to get to a steady state in the simulation. That's part of the problem. It's a very difficult trade-off to choose between those two boundary conditions, but we will come back to that later. Let's first introduce some of the simulation that we have conducted with Thomas Gastine and Alexandre Fournier at IPGP in Paris, and they correspond to this red square. And so we do that with the code magic, of course, and we employed no-slip boundary condition at both the top and bottom of the fluid layer. What else? We reached to lower a little bit the Ekman number to 10 to the minus 6. We can also point this area here, which is also very difficult to achieve with the numerics. They correspond to very highly turbulent flows. And I guess one day it should be very interesting to try to explore this part with some laboratory experiment. whatever. Let's have a look on one of those simulations, and let's start with the smallest Ekman value we have, 10 to the minus 6, and here is one of those simulations where you can observe this beautiful alternating zonal jet that form. There is one which is very powerful here at the equator. And you can also observe these planetary scale waves that form here. There is one which is embedded into these equatorial jets. Well, I didn't explore very well the physics of those waves, but they should be very interesting to investigate, and that will be the job of the next few months, I guess. But they should, it's probably some Rossby waves, and here it's embedded in these jets. You can also retrieve this invariance of the flow, of course, because of rapid rotation. And I think it's worth mentioning again here that because of no-slip boundary condition, you induce two dynamical regions. There is a strong regionalization of the flow here by suppressing the formation of zonal jet in the polar region. So no-slip boundary conditions are so efficient there that you cannot form large-scale features. And in all those simulations I have here, in none of them I find some strong zonal jets that enter really into the tangent cylinder. Well, and that's for this reason, I guess, that we have chosen to compute the spectral analysis I introduced previously outside the tangent cylinder, where most of the kinetic energy concentrate. And actually, what we have chosen as well is to compute the spectral analysis along the cylindrical radius, which is, I think, the right geometry to compute statistical analysis of those jets, because if you go across the jets, then you will capture very well what is the typical length scale of those jets. If you do spherical harmonics here, you will find that this equatorial jet is much thicker than the others, which might not reflect reality. Well, so let's have a look to the kinetic energy prediction. So here correspond to our kinetic energy spectra, and we have the very accurate predictions of what is the zonal and residual kinetic energy thanks to this zonosphere scaling. Yeah?
Did you try looking at the equatorial versus polar Nusselt numbers?
Equatorial versus?
Polar Nusselt numbers? Are you effectively convecting the poles?
No, I didn't play with the Nusselt number. Yeah. Well, but I think you might find a simulation which is very close to that one in the paper of Thomas, no? I don't know if he has a no-slip boundary condition on top and bottom in the 2016, but where the Nusselt is computed for each simulation. But he should have this kind of aspect ratio with the Nusselt number. Now, I didn't play with the Nusselt number, yeah. So yeah, I mean, yeah.
Quick one. So actually the thing you're about to talk about, so the dotted box, so you do it from spatial space then, because if you're cutting off at this cylinder, you really just take that outside wedge.
Yeah.
That's what you're saying for these spectra.
I'm just computing,
From spatial back to a redefined spectral space, essentially, in this direction.
Yeah. Yeah, I just take the equatorial cylinder, right? And I'm doing Fourier and Bessel spectral decomposition. Yeah. Yeah, this is not only in this radius, but at the full equatorial cylinder. Well, okay, what to say about that, except that it predicts quite accurately this kinetic energy distribution. The slope, you can see that it predicts very well the slope, but also the magnitude, which is something very new. I mean, if you have just the slope, it's a good thing, but if you can predict the magnitude, there is a lot of physics behind that. Here you have the turbulent mixing, and here, I don't know what that means exactly to have the zonal energy, which correspond to the rotation rate and the radius, but yeah, there is.
Yeah, the power injection rate, do you estimate that from the?
Yeah, right there. There were another question?
Yeah. What is the Pratt number?
1. Yeah, we didn't sweep into the Pratt number.
7?
Why not 7?
Yeah.
I'm not an expert on the Pratt number, but it's more costly, no? To go into Pratt 7.
Why 7? Well, people think that
Yeah, subsurface.
that's the molecular structure.
Yeah.
Sort of get like water.
Well, but it's not an issue, I think.
Yeah, it's just one there. We didn't explore different. I think Vorka have done that. In this paper, they explored from 1 to 7, prime from 1 to 7.
Well, I don't think we know the material properties anyway.
Well, it's water.
I retract it.
There were another question? No?
Have you done energy flux calculations with filters?
No. I would like to do now, but I didn't. Yeah. I have done that. We have done that on the GCM on Saturn, but I should compute that as well here. Yeah, it would be very interesting to verify that this corresponds exactly to an inverse cascade. Yeah, we will. The entropy and energy flux would be very interesting to compute. All right. So yeah, we have a very good estimate of pi by just computing the mean buoyancy power, so the mean power which is injected by convection. So these depend on the different non-dimensional parameter. And the mean buoyancy power predicts very well what is the magnitude of the residual energy spectra. So it's a very good estimate of pi. And we have also our estimate of the Rhine scale, depending on the typical velocity. You had another?
Yeah, just to better understand. So you say the amplitude is captured correctly, but the Kolmogorov constant you have in front. So you know CZ and CR? Or
Yeah, well, Kolmogorov spectrum is quite well known, and it has been tested in various setups, and they give it to be about 5 to 6, something like that. Yeah, just supposed to be universal. I don't know if it. Yeah, well, it's usually the constant they choose, but also this constant has to be determined. And I took here the constant which have been obtained for Jupiter, and for some other setups. I think in our setup as well we had the same constant, about 0.5 or something like that. So I just used the same one as well here. That's the one. Yeah. It's about unity. I don't know about Daphne, what did you choose, but yeah, it's something about unity. We all put about unity. Yeah, actually we could write without the constant if it's unity, you know. All right, and the Rhine scale also identifies very well what is the energetic maximum in the flow, and this represents the typical length scale of the jets. All right, so yeah, once you add that, you want to move a little bit into the other Ekman value to see if this typical signature of zonostrophic turbulence stand in all those simulations, which means, zonostrophic turbulence is achieved once you have this, the zonal jet correspond to the most energetic features of the flow. But once you move to the other Ekman value, and here it's at Ekman 10 to the minus 5, but I have the same one at Ekman 10 to the minus 4 at the same Rossby here, and you can see that you slowly lose this typical signature of zonostrophic turbulence. So here, it still stands a little bit, but then when you move to 10 to the minus 4, you can see that the residual dominate almost everywhere. So here, it should look like something about 3D turbulence with a very inefficient inverse cascade. And the peak of the energetic maximum pretty much corresponds to the typical injection scale. I was thinking about that when saying it. I don't remember about the picture of that simulation exactly. I don't remember. I don't want to say something wrong. I don't remember. Well, I do have jets at that magnitude, actually. That's the magnitude of the jet. So they exist, but they are very weak compared to the turbulence. Well, all right. So we have shown for different Ekman value, but if it works for one Ekman value and one Rossby number, does it work for the different Rossby numbers? So let's sweep across the different Rossby value. And you can see that here I do represent the residual energy normalized by the magnitude of the spectrum. So if I change the Rossby number, it means that I change the energy input in the simulation. And I retrieve in all those simulations this beautiful k to the minus 5 slope with a good prediction with the mean buoyancy power of the magnitude of all those spectrums. So, well, it seems to work very well for the different simulation, and I can do the same with the zonal energy. As it does not depend on the energy input here, I just normalize by omega square, and I retrieve the same magnitude and same slope for all those simulations, even if there is a little range here that might correspond to the constant, let's say that. But it's pretty well accurately explained by this typical scaling. And you can see that for the different simulation, the Ekman number is the same, so the typical instabilities correspond to the same Kc. However, the Rhine scale change a lot from one simulation to another, and you can see that this Rhine scale represents the jet's width, and this can be, I think this one corresponds to that pattern, and as long as you are increasing the Rossby number, you are increasing as well the size of the jet. So you end with a two-jet solution outside the tangent cylinder. And you can see that this one should be the two-jet, or maybe this one the two-jet solution. I mean, you are almost at the last wave number. After that, you will have filled the complete cylindrical radius here. Okay, so that's a good scaling, and we have a very comprehensive theoretical understanding of this kinetic energy distribution. So now let's have some discussion about the implication for the subsurface oceans. And that's the part of the talk where we say, let's assume that this typical scaling can be extrapolated to more extreme parameters. And there is always a point in which we say that even if this scaling have been tested from observations on Jupiter, so it's quite robust as well for some observation in planetary bodies in which the Ekman number is very low. So we can maybe trust in that one and try to get some prediction for the subsurface ocean. So if we assume that, then we can calculate what will be the typical zonal energy into those subsurface ocean by just integrating the zonal spectrum from the Rhine scale to the viscous dissipative scale. So what we're doing is just an integration of this kinetic energy spectrum, where we use the typical rotation rate and the radius of the subsurface ocean. Well, actually here it's a topographic beta effect, so it is calculated from the topography of the ocean, so it depends also on the thickness of the ocean. And so we can integrate from the Rhine scale down to viscous dissipative scale. So let's say that the viscous dissipative scale is somewhere here, and let's consider that this scale is much smaller than the Rhine scale. Then the formulation can simplify as follows. So the zonal energy depends on the beta parameter and the Rhine scale. However, of course, direct measurements of the Rhine scale are impossible unless we find a way to determine it. But because of the ice crust, we cannot observe what will be the typical Rhine scale of those flows. Maybe there is a possibility that Krista invoked in her talk that if the flow is responsible for the transport of the heat flux from the bottom of the ocean to the top, the zonal jet might be reflected into the topography of the ice crust. That's the possibility, and then we might guess or have some insight about this typical length scale of the jets, and then we can solve it very easily. But that's somehow speculative at that stage, and so we have no information of what could be the Rhine scale of those subsurface oceans. So we have two unknowns and one equation, so we are done. But to tackle this challenge, let's say that we will find, we rather decided to find another energetic arguments to try to find an upper bound to the zonal energy. So it's a bit of pity that we have a beautiful formulation and we cannot have a prediction from that, but let's try to get a constraint on what could be the zonal energy using another energetic argument. And I will reuse the one of Huaming Kang that she introduced yesterday, where we can postulate that the kinetic energy which is injected into the flow, so the mean buoyancy power, let's postulate an equilibrium between the mean buoyancy power and the energy dissipation rate on the large scale. And this energy dissipation rate could carry some information about what is the typical zonal velocity of the jets. Because this, we can estimate it quite easily. It just depends on the flux at the bottom, the energy flux at the heat flux at the bottom of the ocean, and the various studies concerning the radiogenic heating or tidal heating in the mantle can deliver some value of what is the mean heat flux at the bottom of the ocean. So we can estimate what is the mean buoyancy power injected here. So if we consider that we inject kinetic energy corresponding to this pi, considering that this energy is totally transferred upscale and dissipated at the same rate, then we have an equality between the dissipation rate and this pi value. However, we need to know how to estimate this dissipation rate. And it could be various mechanisms that are dissipating energy on the large scale. So I will present here two possible arguments. The first one had been introduced yesterday by Wei-Yin Kang, and she considered that we can use a turbulent drag with CD, a turbulent coefficients that has been calibrated from models of the Earth's oceans. And then if you have this equality, you can guess what will be an upper bound for the zonal velocity. And she provided that for Enceladus and Europa yesterday. And it is about a few millimeters per second for Enceladus and about a few centimeters per second for Europa. However, I don't know, transposing a coefficient which have been calibrated from the Earth is a very good idea, but it's somehow speculative to a high shell that we don't know exactly what's going on there. So we rather decided an alternative to consider that energy is dissipated via Ekman friction. And then you can estimate what will be the Ekman friction, so the dissipation rate due to Ekman friction, and this depends on the Ekman layer, and you can derive a formulation which depends on the viscosity, of course, the rotation rate, and some geometric parameters of the planet. So you can find this derivation in the paper. And then you have a relationship between the upper bound for the zonal velocity and the typical energy input in the oceans. And then you can have other predictions for the different planets. So we retrieve some estimates which are very close for Enceladus to about a few millimeters per second, 2 centimeters per second. We have something which is rather higher for Europa, where you reach about 0.2 to 0.6 meter per second. And this reach up to 0.3 to 1.66 for Ganymede. So that's the prediction that by considering that only Ekman friction at the boundary here is dissipating energy. Yeah?
You could also dissipate energy at small scales. Is there an argument for why the dissipation for the large scales would be a few more power?
You want to say that part of the energy can go there?
There's also a downscale.
Yeah. Yeah, probably here, this split between downscale energy and upscale energy. That's why it's an upper bound. But I would say that viscous dissipation here on the bulk, because this will be viscous dissipation in the bulk, that's much more inefficient than the dissipation on the large scale. For example, if you compute the energy flux from the Jupiter atmosphere that have been done, you can see that most of the energy is transferred upscale.
Then you'll know how much is going in each direction.
Yeah, and then you can get a better partition of that. Yeah, but it's not a bad hypothesis to say that most of the energy is going upscale. But you're right, and that's why it's an upper bound that we can estimate here. But also, it does not take into account eventual topography in the ice crust, so it's just a basic Ekman layer. Yeah. 5 minutes, all right. Yeah, I'm late then. So if we trust that, of course, we can reduce a little bit the boxes in the Ekman versus Rossby diagram by just have another prediction of what will be the typical flow velocity, the typical zonal flow velocity. And it seems that, as it has been already said, that Enceladus is a very rapidly rotating flow, and Titan, Europa, and Ganymede correspond to here. I mean, they're very close to the boundary of weakly rotating convection. We can also use that one to try to have a projection of what will be the Rhine scale of those flows. And the Rhine scale can be estimated here as a proportion of the thickness. And just to sum up it rapidly.
Oh, shit.
Just to sum up it rapidly, because I would like to introduce the last part and the perspective with the magnetic field. But let's say that Ganymede and Europa are a very good candidate for a two-jet solution, or maybe rather for Ganymede, a one-jet solution. But as I have no simulation with one-jet solution, I just put that one as an example. But I think Ganymede is a good candidate for a single-jet solution outside the tangent cylinder. Enceladus is a very good candidate for a multiple-jet solution outside the tangent cylinder. Yeah.
Sorry, single jet, you mean just equatorial prograde, or you mean one returning? Because otherwise you can't conserve.
Yeah.
You need a retrograde if you're going to have one.
One prograde and probably one in the other sense, the top, yeah. And but I have no solution which looks like that. But Krista does have some with free slip boundary condition. All right. And some suggestion for the laboratory. I mean, it seems that it's very relevant to explore that part of the diagram for Titan, Ganymede, and Europa. And I think the lab can do that. So this is a call for future lab experiments. So let's have a rapid look to the observation and the possibility to get a magnetic signal. So I'll try to go rapidly through that, but it's very interesting perspective, I guess. So as you know, the two new space missions will fly by for Europa Clipper, but JUICE will orbit around Ganymede. So it will have a very good coverage of what is the magnetic field and a very good determination of what is the magnetic field there. And it will approach to about 500 and then about 200 kilometers above the surface of Ganymede. So since the ocean conducts electricity, we may ask, does the oceanic circulation produce a magnetic field? And to answer that question, we set up an induction model for Ganymede. So what do we have in that induction model? First, we use the flow pattern from the previous study, and we set the maximum velocity to be about 0.3 to 1.6 as we are in Ganymede. All right, so we have flow pattern, some velocity prediction. Second, we have to reproduce the full magnetic environment of Ganymede. So first, we have to put the Ganymede internal magnetic field. And Kivelson has proposed some magnetic model for this Ganymede internal magnetic field produced from the metallic core here. In the same way, we have to incorporate the Jupiter internal magnetic field, so the Jupiter magnetosphere, and Conerney has delivered a magnetic model for this Jupiter magnetic field, and it has been updated by the Juno mission recently. And the first thing I have to do is to solve the induction equation in this magnetic environment, and the magic code can do that. So I just solved the induction equation, which is the dependence of the magnetic field in time under the action of the flow, U, and under the diffusion of the magnetic field. And one can consider what is the magnetic Reynolds number, which compare the induction, so the ability of the flow to produce a magnetic field, and diffusion, the ability of the environment to diffuse the magnetic production. And if you estimate it, it's about 0.5 to 2.9. So there is a possibility that there is some magnetic production because it's around unity. You can expect that maybe there is some magnetic production from this flow. I mean, that's sure there is, but maybe we will be able to detect that. And as long as I can solve this equation in this magnetic environment, I can predict exactly what will be this magnetic production, and this corresponds to the blue thick line here. But I can also predict what will be the signal that will be detected by the JUICE magnetometer. And here is a typical magnetic energy produced for the different spherical harmonic degrees. So you can see that the observed signal will be, of course, very strong on the large scale because Jupiter Ganymede magnetic field is also a dipolar magnetic field. And this magnetic energy will decrease with the harmonic degree. So I've tested various flow 1, flow 2, with different velocity possibility for the velocity field, for the velocity prediction. So I just plug these 2, 1. So I have a range of magnetic signal that I can consider here. The other thing I can do is to report what is the magnetic signal which is coming from the inner core. So basically, the difference, the gap between the two here correspond to the magnetic production from the oceanic circulation. So there is a magnetic rebound here that can be attributed without ambiguity to the oceanic circulation. But what we want to know now, we want to report what is the detection threshold of the magnetometers. And you can report it to be here, corresponding to this gray line here. So everything which will be above will be detected by the magnetometer of JUICE. However, you can see that in the pessimistic scenario here, it's very difficult to distinguish the magnetic signal coming from the oceanic circulation, rather than in the optimistic scenario, of course, we can get a signal. So what can I do also? It's just to subtract the black one to the blue one. Then I obtain the green one, which corresponds to the signal which is coming from the oceanic circulation. And what you can see that on the large scale, there is always a magnetic signal coming from the oceanic circulation. However, this will be very difficult to separate the source, the one which is originating from the metallic core and the one which is originating from the oceanic circulation. So we know we will have a signal, but in the pessimist case, it's difficult to say if we will be able to separate it from what is coming from the metallic core. Yeah?
Is this computed at the closest approach of JUICE?
Computed from what?
At the closest approach to Ganymede, or at what radius?
This is computed at 200 kilometers above the surface, yeah, so at the orbit of JUICE, yeah. So if we, of course, there is a possibility that JUICE go even more down, I mean, closer to the surface, so then this will lower the gray line to a threshold that will be below, and then we will be able to get there a magnetic signal, yeah?
Sorry, I may have missed it, but what's the difference between the two blue lines?
That corresponds to the different pattern I tested, with different possibility for the magnitude of the velocity field. So I test the pattern with the prediction from the theory. Yeah. Yeah.
Which curve corresponds to which flow?
Well, one is the top.
Yeah. I would say that this one corresponds to the optimistic case. I think so. I don't remember very well, but yeah.
I was just going to ask a sort of honest question. So, suppose you took this observation and you can see, oh, I've got some signal from the ocean. You know, like you're kind of convinced that that's there. You're not just getting the core. Do you actually think, without seeing the simulation it came from, that you would be able to get anything like velocities or flow structure from it, or would you just be like, oh, there is an ocean? No,
well, the idea is to get, I mean, the problem by solving the inverse problem, because this is your question basically, to solve the inverse problem to track back the circulation from the signal, right? So it's not a lot of signals, so you won't have a lot of information concerning the circulation, but we have a very strong a priori knowledge of what is the circulation. So we could just first try to find what is the radial velocity profile, right? And you can try to invert from those knowledge, from this signal, you can to invert just for the radial profile of the velocity field, which will be already a lot, because as you know that if you consider that there are zonal jets, then if you have the radial profile, then you have the circulation almost everywhere. You see what I mean? So
I guess it's somewhat degenerate, but it's not necessarily that different from what people are doing with like the genogravity data, where they take like flow profiles that then fit to the observations. Like
it's not very different from which community?
So you know when they get the jet structure from the genogravity
yeah,
data,
yeah, that's
it's like
pretty
taking flow profiles and seeing which. And I guess you're saying you could kind of do the same.
Yeah, well, that's pretty much the same thing, yeah. I totally agree, yeah. But instead of being from the gravity field, yeah. Yeah, well basically I'm done. That was the perspective, so just a rapid sum up about geostrophic turbulence, but I think we've seen that a lot. Good prediction and some theoretical prediction for the velocity and some perspective about Ganymede tomography. Do I have something else? Yeah, the perspective are those one. Maybe identifies a specific wave. Of course, the waves also can have a magnetic signal, and this is much easier to find if you can get what exactly are the typical frequency of those waves. You can look for them in the magnetic signal if there is some signature. So that will be very interesting to have the typical frequency of those waves, to retrieve them in the magnetic signal. maybe going to the lab again to try to get the more relevant regime and prepare the path toward future tomography of the oceanic circulation would be great, yeah, as we were discussing. Thank you.